Am I recording the right screen? Truly. Just sanity check. We're looking at the curriculum, aren't we? Someone?
Yes.
Excellent, thank you. Okay. Constraint satisfaction problems. So this it sounds more complex than it probably is. Ultimately, what this is when you're trying to solve a problem that has, I guess, multiple, constraints that have to be met before you can say, yes, let's go ahead. There's not always a quick check to verify, that your solution works. Sometimes you have to run multiple, and some solutions are dependent on on how you're solving, future issues. The challenge for today is Sudoku, and it's a really good way to kind of think about it. To anyone who doesn't know what Sudoku is, I can probably explain it real fast for anyone who didn't have to do that in high school or get to play with it in high school or wherever, or just, lives under a rock and doesn't care about it. I'll just pull it up real fast. This is what Sudoku looks like. The way this game works is every row you go through has to have numbers 1 through 9. A row cannot have any duplicates. So a row and a column, work together. So if this has a 5, that means there can be no other 5s this way. There can be no other 5s this way. And then there's in the square, there can be no other 5s this way. They're always solvable. They shouldn't, they should all work. It's not like solitaire. It's, you can't get a bad hand. Sudoku is always solvable, or should be, unless you got a weird one. You got a cheap one or something. This is a good way to think about constraints. What do we say this again? Constraint satisfaction. If you were trying to programmatically figure out what the next number is, you could guess, but that guess isn't, you really shouldn't be depending on that until you verified this row, or this column, and then this square, right? It's kind of temporary guessing / looking down in the future, for what you're going to need to solve for. It also just refers to having multiple constraints. So our two constraints here would be there can't be another 5 on this row. That's our first constraint. The second would be there can't be any repeated numbers. So I think I've got that backwards. No repeated numbers is your first constraint. You're going to check for that. If that solves, you're going to look to see if there's no other repeated integers, numbers in the row. And that's ultimately what it is. There are more examples here that kind of get into a lot of different ways you could really think about this. This is kind of an interesting read I was looking over. There's a lot of different ways to think about constraint satisfaction. The problem they're trying to solve here is no colors can be touching throughout the entire thing. And that seems pretty simple, and a human can look and see that it's wrong, but a computer can't always really quickly just verify, especially with these real simple problems. You have to find a way to explain to it why the next option is or is not okay. I'm not going to run through all these because there is a ton of interesting ways to kind of solve this simple problem. But y'all take a look at that later if you would like. Constraint satisfaction problems have 3 components: variables, domains, and constraints. So each item is going to have its variables. There'll be, domains are all the possible values that could go there. And the constraints are the rules you have to follow. I really like Sudoku as an explanation for this, but that's a hard problem to solve, as you're all going to find out at the end of this lecture. It takes a lot of brain power to kind of solve that. But to simplify that, let's kind of walk through this example. So this example wants us to start out with a list of 6 zeros. 0 is the placeholder. It doesn't count as a number in this list. It can have a range of values, 1 through 9. It's more than 6. And these are the two rules we're going to set. Even indexes must have an even integer, easy. No integer can occur more than once. Seems like something easy you could generate, but when you're trying to solve it programmatically, you got to think about it a little bit differently. So here are our variables here. Any given variable can take on a value in our domain. So an initial solution might look like this. We just slap those in here. Anyone paying attention can see there's issues with this. So 0, 1, 2, 3, 4. Our fourth integer, 4 is even, 9 is not. You can also see that 4 is repeated twice. So do we all agree this violates both of our constraints? There is differentiation. So our first constraint is only worried about the individual values as we plug them in. That is called a unary constraint. Unary? I didn't go to college. I'm not sure. I think it's unary. The second constraint is more about the wider context. And we're going to call that the higher order constraint. So does it work here in this spot? Yes. Does it work for all the other things we need to think about? That's the higher order constraint. Following both, we can see it's an issue. And as I kind of talked about, a human can look at that real quick and say, yeah, that's easy to, that's wrong. But we need to think about how to programmatically solve this. So I'm actually going to, I want to pull up VS Code here in a bit to show you something. But for now, we're going to do it just reading this. So we could iterate through all the indexes and maybe that would be fine. We can also just randomly generate numbers. So we'll do that, this way. Imagine we're kind of running through a loop because that's what this is sort of setting up. So our first guess is 4. Just give me a random number and we're going to plug it in and see if it works. The current index is 0. These are our variables. So we plug in 4. That works, right? 0, I don't know if 0 is considered an even number, but if it is considered an even number, we're good because 4 is an even number. 4 is not repeated anywhere. Don't worry about the zeros. They're not real numbers in this situation. So anything that's not a 0 can't be repeated. So here's our second guess. 9. It's going to go in the 1 index. Plugs it in here. 4, 9. Doesn't violate our unary. Doesn't violate our higher order. We're still good. We'll go to the next one. Random guess is going to be 9. Oop, wait, hold on. I don't know why. So I actually struggle with this a little bit. Is there something that says we need to have all of them? We're on a roll, but wait, aren't we forgetting about our second constraint? We need to make sure our updated variables doesn't contain any duplicates. So let's redo that last step. What are we redoing here? Oh, we're not forgetting anything. It just didn't put that in there. Okay, so we matched the first, and now we're matching the second. Sorry, that's written kind of weird. We're not redoing the step. So yeah, we're good. It's odd. Yes, we're good. There's only 1 9. That's broken down to the bare basics. All right, random guess number 3. 3, current index. 2, constraint 1 fails. Guess again. Why does constraint 1 fail?
It should be even.
That's right. It should be even. Restart. Random guess 4. So we're going to plug a 4 into here. Constraint 1 passes, right? It's even. Guess what fails, y'all? Our higher order our higher order constraint, because we've got 2 4s. So you can see from this highly complex example, how complicated this can be. So we're going to have to basically take a step back. This sounds good for recursion, but there's other ways to do it. While loops, recursion, anything that can kind of undo previous work. So we recovered from the failure. Something that seemed like a good solution initially. So what it's saying here is, yeah, it worked for the first and it seemed like a good solution. Then we go to a higher order constraint and it's not a good solution. So we have to build a backtracking method. This implementation here is a pretty good implementation. So I'm going to copy this and paste it on VS Code, and I'm going to play with it just a little bit.
Can I ask you something real quick?
Yes.
The high order constraint in our case, what makes that condition number or constraint number 2 a higher order? Because to me,
right, because it is not based off the individual. The unary constraint is based off of, hey, I am in an even index. Am I an even number? It doesn't care about anything else. It only is looking at itself, right? The higher order constraint is saying, hey, are there any more? Are all of you, individual? Am I the only 4 here? It's higher order because it's looking at the wider picture and verifying that your unary hasn't, violated that. So you got kind of your, gotcha. Cool. And this is a good job. I do like this example here. This kind of walks through it. For this, we're going to import random and then rand int. If you want to do random integers in Python, that's how you do it. We're going to set a unary constraint. So this should, track with what we've kind of been talking about. You could consider everything we've done before this kind of pseudocode for this. We're going to check the index. Remember, the value and the index are 2 things we want to look at. Ooh, don't scroll that fast. If the index modulo 2 is equal to 0, do we all know what that means? Does anyone not know what this means? It's okay if you don't. I've never taught you modulo, so the other instructors may have had some holes. Modulo is the remainder. So an even number should never have a remainder. This is how you solve FizzBuzz. So we're going to check if the index is even, then we want to see if the value is even. We're good. However, if the value is not even when the index is even, we're going to return false and say, no, that's not going to work. Otherwise, return true. Basically, if we're on an odd number, who cares? Just spit out true. For a higher order constraint, we need to check everything. So a non-zero, what this is doing, does anyone know what this is called right here in Python? What this highlighted bit is, what it's doing, what it's called?
List comprehension?
Yes, it's list comprehension. We're building a list out of a list. We're saying rules for the list to be built from the old list. So for variable, for variable, and variables, if your variable is not equal to 0, you get to be part of this non-zero family. The return statement here, we're going to be checking this new list here, non-zero, versus a set of non-zero. Set, if y'all haven't come across that, I feel like you probably have. Just a reminder, if you set a list, that list is going to remove all duplicates of itself. So it'll just make the list shorter if there are any duplicates. So if our non-zero list is equal to the duplicate removed list, the set list, then we're good. Otherwise, we're not good. And we won't return anything. Or actually, no, this return is going to do true or false. My bad. I read that wrong. So double equals, if these are the same length, true. If they're not, false. Sounds good. That sounds like a good check for me. So our unary constraint check right here makes sense. Higher order constraint looks good to me. This last one here is going to, create the list out of whatever we plug into it. This is going to take in variables. This is going to set a current index of 0. That makes sense. We want to start at the beginning of the list. Remember, we are trying to, just as an example, print out something that kind of looks like, did it give us a fully done one? Or do I have to type it all out? No, it didn't. Oh, yeah, it did. Well, no, that's the wrong one. Sorry, I thought I just copy paste that. No duplicates. So let's say that one's like 5, and we'll say this one's like 2. So that's an example of what we're trying to build. So let's call this function. It's going to take variables, and we're going to keep track of our indexes. We're going to solve this left to right. It's going to set a domain from 1 to 9. This is just building a tuple. We're just using this. If this is feeling extra complicated, because I think it's adding a few different things, it's just displaying how you can use tuples. All this is doing is it's going to plug in 1 through 9. And what that's going to do for rand int is, hey, give me a random integer between 1 and 9. The way this is solving it, though, is setting this domain up here as a tuple and then displaying how smart we are because we use args. So, hey, give me that tuple as args. Rand int is going to take a random number between 1 and 9. So as we kind of talked about, it's going to generate a random number as we did before, and which is this, the guess. It is going to take that, plug that guess into the current index. So let's follow it up here. Let's say this guess is actually this 1 here. So it guesses 1, runs up to the check index. It's got a 1, and remember the value is 1, index is 0. If the index modulo 2 0, yep, that should pass, I guess. If the value modulo 2, nope, doesn't pass. So, or sorry, that's not true. So just exit out of here. False, right? Wait, hold on a second. Oh wait, 0 is not considered an index. So yeah, 1 is fine. My bad, guys. So 1's okay. We don't count that as an even number. So it's just going to skip through that. It's going to say, no, the index is, not modulo. That's fine. Back to here. The variables are going to be the current index, which is, oh goodness, right now is 0. And we're setting that equal to guess. So we're basically plugging guess in here at 1. So we've solved for our unary constraint, and we're going to iterate and go to the next. Now we're going to do our higher order constraint. Check reps in variables. Check for repeats, basically. It's going to run up here. It's going to spit the list out. It's just going to have a 1 because we took all the zeros out. It's just going to be a 1. The length of 1 is equal to the length of 1. Good to go. Then we're going to recurse, and we'll just keep running through this. We can see this run in real time if we would like to, and we will, just to prove that it works. I was playing with this earlier, and I didn't dig in too deep. Maybe we can dig in as a class if y'all want. Sometimes this it backs itself up in a corner, and it runs a few numbers in a bad order. I guess it runs out of evens or it runs out of odds with a range of 6. But we'll see that. So let's just print this. Cool. That let's see if this is right. 2 is good because I don't know if it's counting. Okay, so that pretend list I had was actually bad. So we're counting 0 as an even going forward. This is giving us even, even, even. I don't see any repeats. This looks good to me. What else did I want to show you? I did want to point something out. So this is recursing and it's solving, and it looks like it's just if you were just to see this. Oh, look at that. We found a broken one. I maybe want to troubleshoot this later, just to see what's going on, because unless anyone's smart enough to figure it out by looking. Oh, I didn't talk about this bit here. So if we fail the check reps, because this is saying, hey, if we get a false back on this, like you gave me a number that we've already put in there, it's going to reverse the index. We're going to go back by 1, set that variable to 0, and recurse. So that's the backtracking we were talking about. We said, hey, actually that doesn't work. Get rid of that one, run back through. Because we're generating random numbers, this is not a constant. Okay, well, it's a constant solve time, but it's actually not though. It's a random solve time, and I know it sure looks like it's doing it exactly the same amount of time every time. But speaking of time, we can put time in front of anything we do here on this terminal, and you can see there are different solve times for this. So our actual solve time on some of these, what is that, milliseconds? Less than milliseconds. We've got different times for the total amount of, like, for the total solve time. Basically, it took the system 13, I'm going to say milliseconds because I don't remember off the top of my head. The user 32, and then the full total time here was 0.047. But this one was a little bit slower. This one was a little bit slower. This one was a little bit slower. That could be due to processes that are running on my machine. Or it could be something else. I want to prove it with setting a counter. So where do I want to put this counter? I think I want to hear. Best way to do that. Anyways, well, it doesn't matter. Just for sake of showing what's going on here. Oh, it's not iterating. Why isn't it doing that?
Don't you have to put it in the recursive function on 23 so it keeps the count and doesn't go back to 0?
Yeah, that's where it probably should go. Over here. Let's try that.
You don't have to put it in the parameters of the recursive function so it keeps the count? Because when it's starting back at 0, isn't
it? Yes. Yeah, good. That was a test. Cool. So let's plug it in here then. Oh, that one broke. Look at that. So we did find one. This recurs 995 times for whatever reason. This one got it done in about 10. This one got it done in about 12, 22, 19, 9. So this is randomly generated. It can guess wrong. The number of times it guesses a number we already have, we could probably speed that up by saying this random number. Where is it? Yeah, we could probably speed that up by saying, hey, if that number already exists in this list, you can't use it, give me another one. But as it is, it's just giving a random number somewhere between 1 and 9. If it works, it plugs it in. If it doesn't, we come back around and recurse. But I just want to show you all that it is, in fact, taking a variable amount of time to run through these because we're just generating a random number each time. It's checking to see if the unary is satisfied, checks to see if the higher order constraint is satisfied. If either of those fail, it recurses. When none of them fail, we get true for everything. Everything looks good. It is going to spit out that final list here because there's no more zeros left in the variables. It's just going to give us the variables back. Yeah, that's where that should go. Am I going to look like an idiot in front of y'all? Oh, no, there it is. So that's what I probably should have done. Look how clean that is. So there it is. There's the counter. Any questions while we're in it? Is that simple enough? Too complicated? Do I need to walk over any part of that? My finagling with it make it more complicated than it needed to be? Maybe. Ah, see, told you could be more efficient. Anyways, oh, hey, you know, when I was practicing for this, I got to about here, and now I'm telling you all stuff that's already here. There's a problem in here. It's known. You can find it if you'd like. Otherwise, if there are no other questions, I'm going to stop recording, and then we'll talk about Sudoku. All right.